Mr. Heffron here, and here's a short video on Kirchhoff's voltage law. Kirchhoff's voltage law states the sum of the potential rises equals the sum of the potential drops in a circuit. So in this case here, we have 1, 2, 3, 4 D cells in series, each 1.5 volts. So we got 4 times 1.5 volts. So that's 6 volts of potential rise, or being put into the system. And then coming out, we got this load dropping the volts by 3 volts, this resistor by 2.5, and the lamp by 0.5. 3 plus 2.5 plus 0.5 is 6 volts. So 6 volts comes in, 6 volts must be used up. So in a series circuit, each load drops the electrical potential, and the electrical pressure that goes in must come out. This is really just the law of conservation of energy. The same is also true for water circuits or for plumbing. In an older home, you may notice that if you turn on a faucet, that affects the pressure in the shower. So in this case here, we have a D cell providing 1.5 volts. And then later, this resistor, the blue resistor, drops the voltage by 0.5 volt. And then down here, this lamp drops it by 0.4 volts. So how many volts must this resistor be using? So we got 1.5 coming in. 0.5 plus 0.4 being used, which is 0.9. So 1.5 subtract 0.9 is 0.6. So this resistor here must be using 0.6 volts. In a parallel circuit, each load has its own line, so each load has the same voltage as the source of the parallel circuit. This is also true for water circuits in newer homes, where the faucets and showers do not affect each other's pressure. So in this case here, we got a car battery providing 60 volts. And then what happens is the electrons come out of the battery, and then when they get to this point here at the junction, the electron right here will push the electrons in front of it this way and this way simultaneously. And then when the electron gets to here, it'll push the electrons in front of it this way and this way simultaneously. It's kind of like a crowd of people behind people in front of the doors at an arena or a stadium. They're going to feel the pressure from that crowd to go out either door regardless. And so, in this case right here, we have the resistor, the toaster, and the lamp all have 60 volts. In a combo circuit, a little tricky, you have to know when it's parallel, when it's series. So to start off, we start off with electricity flowing from the battery, and it has to go through this resistor. And then it has to go through this resistor. So there's no way to split up the current at this point. So this is definitely a series circuit. And then as it comes around to this yellow box here, you can see there's a junction, there's a split in the line. So now the electricity can flow through number 3 or through number 4. So the electron right here would be pushing the electrons this way and this way through the toaster and the lamp equally, with equal amount of electrical pressure or voltage. So first of all, we can find out what the voltage of the toaster is, knowing the fact that in a parallel zone, the voltage must be the same everywhere. So the volts for the parallel zone equals the volts at number 3, which equals the volts at load number 4. So 4 is equal to 3, which is equal to P. And then for the series circuit, it's supposed to build up. So here we got 9 volts going in. We used 3 volts so far. The parallel zone uses 4, so that's 7, which means the voltage at number 2 must be equal to 2 volts. Oh, I see a little typo there. Okay, so KVL works for water circuits as well. So for example, here we got a water tower in the city providing 55 pounds per square inch of water pressure. So the water comes through and then it splits up right here. So there's going to be 55 psi pushing the water all the way down to the shower head. So we can figure out what the psi is for the shower head. It's going to be equal to 55 psi. And then going through this series circuit, there's going to be 55 psi pushing the water this way. So if the faucet here is using 10 psi pressure, and this faucet is relieving the system of 15 psi, then how much psi must be going through the toilet when it's flushed at this point? So we can find out. 55 goes into the series circuit. 10 psi is being used. There's another 15 psi being used. So the toilet must be getting 25 psi. So you see once you know Kirchhoff's voltage law, you also know how to do a bit of plumbing math as well. So Kirchhoff's voltage law states the sum of the potential rises equals the sum of the potential drops. A battery, generator, or some other source of electrical potential provides a potential rise. A resistor, a lamp, or a fan motor, or some other load provides a potential drop. And really, Kirchhoff's voltage law is really the law of conservation of energy. So the voltage that comes in must come out, just like the energy that goes into a system must be equal to the energy that comes out. I hope this helps. Thank you.